So I would like to thank John. Are we early? Are we early? We're supposed to pre-warn? Okay, so thanks, John, for the invitation. This is my third spring lecture series. I was here last year, and here 4 years ago. It's always a pleasure to come back. It's a really nice series. So I'm going to talk about some very specific question. Grace giving us so far a grand overview of many things, and so this is a very different focus. There's actually just one theorem that I want to discuss. And it's got to do with these edge metrics, which we've heard about, although, as you've seen, there's a complete and an incomplete version of these, and I'm going to be talking about the complete setting. So the main result that I want to discuss is a generalization of something that's been known for some time in a special case. So I want to start by explaining the special case as an introduction of what the result is. So we start with a manifold with boundary, and we choose a defining function as a boundary. So function vanishes the first order at the boundary is positive on the inside. And then there's a notion, it's actually probably one of the first, at least certainly in the Melrose School, of these that were studied systematically, the conformally compaq metrics introduced by Rafe and Richard Melrose in the 80s. So a conformally compaq metric is a metric on the interior of the manifold boundary with the property that if you multiply it by the square of the defining function, that extends smoothly to the boundary. Okay, so there's a special class of these called the asymptotically hyperbolic metrics, which are ones that have a one normalization at the boundary. So if you look at dx, that's defining a one form at the boundary, and x squared g is a metric that's smooth at the boundary, so you just take the norm of that, and that smooth metric and repart it at b1. And the point is that's an invariant of the metric, because if you rescale x, then dx and x squared g scale in ways that cancel, so that's independent of the choice of defining function. So another thing you get when you have a conformally compaq metric is that you get a conformal class of metrics on the boundary. So if you look at the restriction of any one of these smooth metrics to the boundary, you get a metric on the boundary, and when you change the defining function, then that just scales, so you get a conformal class. And that's called the conformal infinity of the metric. Okay, so those are just invariant things associated with it. So then the result I want to talk about is a normal form. So if you have an asymptotically hyperbolic metric, then if you choose a metric in the conformal infinity, so a metric with the conformal class at infinity, then you can make a diffeomorphism from a product of the boundary with a little interval to a neighborhood of the boundary of the manifold, which is the identity on the boundary. And it has the property that when you pull back the metric, you get this nice normal form. So we have dx squared plus h sub x over x squared. And h sub x is just a one-parameter family of metrics on the boundary. So there's no cross terms of dx with a boundary piece. And the coefficient of dx squared is 1. And the one-parameter family h sub x depends, it starts out being the metric in the conformal class, which it shows. Okay, so this was proved, I proved this with Jack Lee in a work on a boundary value problem for metrics like this in 91, and then Joshi and Savaretto were unaware that we had done this and gave a different proof in 2000. So let me point out a couple things about this normal form that are going to be important. So the first one is there's not a unique normal form. We made a choice of a representative of the conformal structure, and we got a one-parameter family h sub x. So if you change the h, you're going to get a different normal form, which will be diffeomorphic to this one, and the h sub x for the other one will start with some other metric. So they're not unique. So one important consequence is the fact that there's existence, but then it's really important for the applications to know that the set of normal forms is parameterized precisely by this choice. So I'll indicate, just quickly mention some of the applications that use this. So we know exactly what all the normal forms are and how to parameterize them. So the main reason this is important is that the metrics on the inside are really often only determined up the diffeomorphism, and this parameterization of normal forms is how one mediates between the conformal changes on the boundary and diffeomorphism changes on the inside. So this is a fundamental interplay in the study of the geometry of these metrics and in conformal geometry of the boundary and the relationship between the two. So one thing that one wants to do where this plays a crucial role is to define the renormalized volume of these Poincare-Einstein metrics, which I'm not really going to describe, but they're a special class of these asymptotically hyperbolic metrics. So the way that works is you want the volume of any one of these is infinite, and you want to renormalize it by taking an exhaustion near the boundary that comes from this. Just look at the set where one of these defining functions x is bigger than epsilon when epsilon goes to 0. And you can do that, but the way that you do that depends on which defining function you choose, and you've got to decide whether or not this is independent of that choice. And to do that, you've got to use these different normal forms and study how they vary. Sometimes the renormalized volume isn't invariant under these changes, and there's conformal anomalies that are important in physics theories. I mean, the way you understand them is via this. And then there's one other application. There's objects on the boundary. This really comes from a slightly different setting than an ambient metric realization of these Poincare metrics. But there's things called conformal curvature tensors, whose conformal transformation laws depend on actually the Jacobians of the maps that go between different normal forms of the boundary. So this is all, the point is there's many applications. It's an important concept. So what I want to do today is to talk about normal form for a larger class of metrics, these edge metrics, with similar kinds of potential applications in mind in the future. I'll mention the examples that are leading to these considerations. So it's motivated by this idiocy, key correspondence, and its joint work with my former student, John. Okay, so we've heard already quite a few lectures about edge manifolds. Unfortunately, most of us use the same at least notation. So we've got x, y, and z. That'll be familiar. So we start with a manifold with boundary. My point of view is slightly different. I'm going to think of the edge manifold after you've done the blow-up in the sense of Rafe's presentation. So you start with a manifold with boundary, compact boundary, and we suppose that the boundary is the total space of the fibration. So that means we've got a projection from the boundary to some compact manifold Y. The fibers are all isomorphic, diffeomorphic to F, and this is locally trivial. So the boundary of X just has a foliation with these nice fibers projecting down to Y. And then you say that this is an edge manifold because this encodes the edge structure that we've been hearing about. I'm going to spend a lot of time, and probably half the lecture, describing for metrics some of the geometric structure that's naturally associated with this. So the starting thing is just that there's clearly a vector bundle on the boundary, or over the boundary, which is the vertical bundle, which is just the kernel of the differential of this projection. And that's the tangent bundle of these fibers. So I call that V. This is the vertical bundle of the boundary. And then a vector field is an edge vector field if its restriction to the boundary is tangent to these fibers everywhere. So it can't point out, it can't point in the y direction, it's just tangent to the fibers in the boundary. Okay, so we've already seen the local coordinate description in these other talks, so again, this is familiar. So we're going to have x, y's, and z's. So these are going to be local coordinates near a point on the boundary. And x is always a defining function. The y's are coordinates upstairs with the property that if you restrict them to the boundary, they're the lifts of local coordinates on the base. So that's the same thing as saying basically that on the boundary, they're constant on the fibers. So these are just the pullbacks of coordinates and then extended off. And then the z coordinates are ones whose restriction to each one of the fibers gives local coordinates on the fibers. So that's the same x, y's, and z's that we've been hearing about. Okay, so then the edge vector fields, of course, the differentials of the z's are the differentials, let's see, the differentials of the, well, if you've got a vector field that on the boundary is tangent to the fibers, then on the boundary it's just got to be a linear compilation of the dz's, because the ddx and ddy are not tangent to the fibers, so the edge vector fields are the span of x dx, x dy, takes advantage of the boundary of the dz's. Okay, so as Thomas explained this morning, there's a vector bundle that one can associate to this. It's a little confusing the first time you think about it. So this is the edge tangent bundle. And this is a vector bundle on the whole manifold with boundary whose sections are these edge vector fields. So in effect, what you're doing is declaring that x dx and x dy are no longer zero at the boundary. I mean, as standard vector fields they are, but now we just declare them not to be and just take them to be sort of if you like, algebraic objects and take linear combinations of these to be elements of this edge tangent bundle. There's other ways to describe it. But, okay, so that's going to be a fundamental thing. We just declare these to be linear independent. Now there's an evaluation mapping that maps the edge tangent bundle to the tangent bundle. It just evaluates your object at the point. On the inside, this is just an isomorphism of the fibers, but at the boundary, its image is just the vertical vectors because x dx and x dy vanish when you look at them as regular vectors. So we've got this natural evaluation map whose image is the vertical one. That's going to come up. Okay, so edge metrics. So first thing is we dualize. So we look at the dual of the edge bundle. So the dual basis to what I wrote before was just the dx over x, dy over x, and the dg's. And then an edge metric is just a smooth, positive, definite section of the second symmetric power. So it's just a positive, definite thing built out of these basis vectors in local coordinates. So we can write it. I'm going to give invariant definitions of everything I'm doing, but it's always good to see what these things mean in these coordinates to get some intuition. So the edge metrics, this is just write down your basis, so you just multiply this out, and the G-bar matrix that comes up here is just smooth and positive. It's an arbitrary, smooth, positive, definite metric up to the boundary. So this precisely describes the way the metric is singular at the boundary in terms of the boundary fibration structure. So if you restrict the metric to the inside, then of course we just get a usual metric, and then it's singular, like I just said. So I want to just mention two motivational special cases here. So the first one is where the fibers are points, and that just means there's no dz variables. And so if there's no dz's, then you've just got a conformally compact metric, because the x over x and dy over x just on both sides just pull out an x squared. So there's no z variables, and that's that special case. The other special case I want to look at is the other extreme is not what I'm going to look at. There's another extreme where the base is zero-dimensional. But I want to look at the examples that are really motivating where I'm coming from here. And these are the examples that come from physics. And these are product situations. So the manifold itself is the product. It's just not only on the boundary do we have a product, I'm actually going to take the whole manifold to be a product. So M is a manifold with boundary, and F is a compact manifold. And then of course, when you take the boundary of M across F, that's a trivial product fibration, and so this naturally inherits an edge structure. But we just throw away the product structure on the inside conceptually, but to get an edge structure. But we can remember that it's there. So then we can take an edge metric to just be a product metric of a conformally compact metric and an arbitrary metric on the compact fibers, and that is an example of a product edge metric. Okay, and so most of the examples that come up in string theory are examples where you've actually got products. So you always hear about ADS5 cross S5 and things like this. So you've got some compact manifold and then some conformally compact space. So we're interested in generalizing this to a more generalized setting. So these ideas. Okay, so there's a few geometric objects that one naturally gets when one has an edge metric. So suppose you've got an edge metric, we pick a defining function. What I'm going to do now is, the first thing is to describe the analog of the conformal infinity that we have for a conformally compact metric. So if you look at x squared times g, like we did before, then at the boundary, that's going to annihilate the vertical vector field. So just to see that, let me run back just a minute to remind you. So we're taking x squared times g. So if you run back to the formula for g, if you multiply this by x squared, then just put one of the x's on the first vector and the last x on the last one, and then everything becomes smooth. So you get dx, dy, x dz. So when you evaluate at x equals 0, the dz's drop out. And the metric on the boundary, x squared g on the boundary, doesn't have any dz's at all. So that's why it makes the vertical vector field orthogonal to everything. So that's what this says. So that means that you actually get a metric on the quotient space or the tangent space to the whole manifold on the boundary modulo the vertical. That's a annihilated space. So you get a metric, and then that, just like in the conformally compact case, that scales when you change your defining function. And so we actually get a conformal structure now on the quotient of the tangent space by the vertical space on the boundary. Okay, so that's the analog of conformal infinity for edge metrics. Okay, now I want to introduce the analog of this dx squared, the thing that was supposed to be 1 for asymptotically hyperbolic metrics. So we look at dx, that annihilates the whole tangent space of the boundary, particularly annihilates v. So we can look at it as a element of the dual space of this quotient, and the x also gives us a metric, not just a conformal class, this metric on the boundary. So we do just what we did before. So now just view everything as defined on this quotient space, and once again we get some number because the scalings cancel out just like they did before. So this is independent of x. So this is an invariant of an edge metric. So we'll say the edge metric's normalized if this is 1. So this is the analog of asymptotically hyperbolic. So I'm just going to call it a normalized edge metric. Now there's something else you can do, and this is important in the edge case that doesn't have, it doesn't give anything different in the conformally compact case. So you can also look at dx over x. So that's, just remember that we regard that as a smooth section. That's the dual to x dx. So that's a smooth section of the edge cotangent bundle. The metric is a metric on that space, so we can just look at the norm of that with respect to g. Everything is smooth, I mean, viewed as edge things, so that's some function on the boundary. And it turns out that's not the same as, these are two different things in the edge case. So we say that x is a normalized defining function relative to the metric if this function is one like that. So there's two different things you can do. The first one's independent of x, the second one depends on it. So to see why, let me just show you why. These are different conditions. Like I said, the first one's independent, but here's how we can see the second one depends on x. Just suppose we rescale x, and you calculate the new dx over x, so you get the old one plus dA over a. And now in the conformally compact case, dA over a is smooth up to the boundary, so dA over a is smooth, and as an edge one form that vanishes at the boundary, and so you get the same thing that you had up above. But now dA over a is not, if it's got dz pieces in it, then that doesn't vanish at the boundary, and there's no reason that its length is going to be the same as you had before. So those are two different conditions. So, like I said, these are all invariant descriptions, so let's make this explicit. So here's our formula for the metric. Let's just see what these normalization conditions really mean. So remember, we've got a positive definite, this is an arbitrary smooth positive definite matrix here, this in the middle there. So to get the first condition, what we do is we look at the conformal infinity. So we multiply this by x squared, so that gets rid of the x's. And then when we let x be 0, the x's drop out because they had an x multiplying them. Remember, you put one x on each one of the factors. And so if you just write this out, then the metric that you get on the quotient space is just represented by the upper 2x2 block in these pieces. So that block is the representation for the conformal infinity. So what we wanted to do is calculate the length of dx squared. So we need to calculate, remember the dual metric on covectors, you take the inverse. So you take the inverse of that matrix, and then the upper left corner is the length of dx squared. So the condition that the metric is normalized says that that number is 1. So you take your whole matrix, you just look at the upper 2x2 block, take its inverse, and the upper number has to be 1. So that's that condition. On the other hand, let's look at our other conditions. So now we look at dx over x. So that's a dual basis vector in the full frame. And then that's viewed as smooth when we look at the edge metric itself. So we have to take the inverse of the whole matrix, and then the number we get in the upper left-hand corner is equal to that. So x being normalized means that this number is 1. So clearly those are different things. If the inverse is just going to give you a different number in that upper left block, depending on whether you look at the full matrix or just the piece of it. Okay, so the first condition is independent of x. This one depends on the choice of x. It's independent of the y's and z's, which also enter into this matrix, but it does depend on x. Okay, so that's our normalization condition. So now the next geometric invariant that an edge metric has is there's an induced metric on the fiber, on each fiber that has an induced metric. So the way that works is like this. So we start with our metric. So the edge metric, by duality, edge metric is a metric on the edge tangent bundle, but by duality we get a metric on the edge cotangent bundle. It's just the dual metric. Now, an inner product on a vector space is a symmetric second symmetric power of something in the dual space. So a metric on the cotangent bundle is a symmetric thing in the tangent bundle itself, a section of that. And so remember, we can evaluate, we had this evaluation mapping that takes the edge tangent bundle to the usual tangent bundle. It just evaluates, so that means the x's that multiply with the x and the dy pieces vanish. So when we evaluate that, we get a smooth section of the usual tangent bundle, but it only has vertical pieces in it. So on the boundary, we get something that degenerates, and it's actually a non-degenerate element of the second symmetric power of phi. And now we dualize that again. That's a non-degenerate thing, so that is the same thing as a metric on V star. We dualize that, and we get a metric on it. So every fiber, this is a completely invariant thing, every fiber has a natural Riemannian metric on it that comes about via this procedure. Okay, so conclusion is that we get a metric on each fiber. Okay, so again, let's write this concretely. So we started with the inverse metric for the edge metric. So the inverse, the G uppers means you take the inverse matrix and you put the dual basis. Now we evaluate that, so that you just set x equal to 0, and all you get left is the bottom right block. So that's the thing there, the section of S2. That's non-degenerate, so you have to take its inverse to get the actual metric. So the actual metric on the fibers is obtained by taking the original matrix, throwing away everything, taking its inverse, throwing away everything but the bottom right block, and taking the inverse. And that's a completely 100% invariant thing to do. You get a metric on the fibers. Okay, so next thing is there's an exactness condition. So we've got a defining function. Let's run back through this. We look at dx over x. So that's a smooth section of the edge cotangent bundle. So we've got a metric on the edge cotangent bundle, so we've got a duality, so we can turn vectors into covectors and vice versa. So this section of the dual bundle, by duality, gives us an edge vector field. It's just a dual with respect to this edge metric. And now I evaluate that edge vector field, and once again, I get a section of the vertical bundle on the boundary. So that's a vector field on each fiber. And now I dualize that with respect to the metric on the fibers that came from the previous slide. So we've got an invariant metric on each fiber, so I look at the dual for this vector field, and I actually get a one form I get a one form on each fiber out of a defining function in a completely invariant way. Now you see what happens when you change the defining function. So we've seen this. When you change the defining function, you get dx over x plus dA over a. And now that's d of log a. And now you've got to run through what I just said. So you have to look at the vector field dual to that, evaluate at the boundary, and then take the dual to that. When you run through that, there's actually, because when you evaluate at the boundary, this piece, the inverses just cancel. And if you run through that, what you deduce is that the corresponding one form just changes by the exterior derivative in the vertical directions of this log a. So once again, we've got given an x, we get a one form on each fiber, and now we see that when you change x, the one form changes by a globally exact form. Right? So alpha changes by an exact form. So that means whether or not the form alpha sub x is exact is independent of x. So we say that the metric is an exact edge metric if for its defining function there's a smooth function everywhere on the boundary, so that on each fiber the corresponding one form is the vertical derivative of f. Okay, so it's just an invariant condition. And by the observation I just made, if that holds for one x, it holds for all independent x. Okay, now if that's true, then you can always choose an x to make this one form be 0 just by rescaling it by the function that this is d of. So you can just always scale that to be 0. And so we'll say that if you've got an exact edge metric, that a defining function is related to it if you get a corresponding one form of 0. Okay, so this is an invariant thing. So in this case, you can change the related defining functions are determined exactly up to scaling by a function that's constant on the fibers, because the dv has to be 0, so on each fiber you have to vanish. Okay, so now this, let's make this explicit first of all. So again, let's go back. Here's our inverse metric. So if you want to see what's the corresponding vector field, well, you basically have to just look at the first the first row of the matrix times your, because we're looking at the first vector. Dx over x is the first vector in our dual basis, so we just take the first row times the basis vectors, and so this is the formula for x of x we get. And so x being related says that when you evaluate that at the boundary, you get 0. So when you evaluate that, you get the g's. So the condition that the x, this defining function, is g related just says that the upper rightmost block of the matrix is equal to 0 everywhere on the boundary. Okay, so this allows us, remember we had our original thing we did was we constructed this conformal infinity out of our conformal class. So we did that by multiplying our metric by a defining function and got a metric on the boundary. But now we have a special class of defining functions. We've got an exact metric. So we get what's called a reduced conformal class. So a class of metrics, but where the scalings are allowed only to change by things in phi. Okay, so I'm just writing what I just said. So if you've got an exact metric, you can restrict to representatives of the conformal structure that come from these G-related defining functions, and you get a reduced conformal class. The metrics are up to scale by constants. Okay, so let's see, one little remark. This is not terribly important, but it's the way I've been describing the conformal structure is a set of metrics on the full tangent space to the boundary modulo the vertical space. In the conformal infinity that I described for asymptotically hyperbolic ones, we use the tangent space just to the boundary to get the conformal infinity. So those are basically the same. I mean, in this setting, you can look either way, as long as the dimension of the base is positive. If it's 0, then the tangent space to the boundary mod B is 0-dimensional. It doesn't make any sense. But otherwise, you can look at this either way. Okay, so finally, triangle had to do with normal form. So let me describe what normal form means. So now I'm going to have an edge metric on a product space. So boundary of x is just a fiber manifold, the way we had before. This product has a natural edge structure. And so an edge metric on here is in normal form. If you can write it in an analog of the normal form we have for asymptotically hyperbolic metrics. But now K is a smooth section of the edge cotangent bundle on the product that has a property that on this product, of course, we've got a dx and an x dx canonical on the product space. So that annihilates K everywhere. So K has no x dx, has no dx over x's in it when you write it out. That's one way to say it. So there's no cross terms, just like before. So this is equivalent to saying that these zeros mean you have no dx over x terms. And the 1 is just saying the coefficient of dx squared over x squared is 1. So that's an analog for these edge metrics of the normal forms I talked about in the asymptotic hyperbolic case. Okay, of course the k is just the part on the bottom. I just wrote down what it is. So the dx squared over x squared is the first 2 rows, and then that's the corresponding k. And notice that any metric of this form is necessarily exact. It's exact. You just run through all the little explicit computations you did, or just check the invariant definitions. I mean, it's exact because if you take its inverse, the upper right corner is 0. It's normalized because if you take the inverse, the upper left thing is 1, either of the whole matrix or the upper 2 by 2 block. So this is any metric in normal form is exactly normalized. And the defining function in the product is a related defining function, and it's normalized. And notice that this defining function actually gives us a representative of the conformal infinity, just like in the asymptotically hyperbolic case, because if you multiply k by x squared and restrict to v, the dz's drop out, and you just get the g bar alpha beta. So that is any metric and any edge metric in normal form can be restricted to the boundary on the quotient, and gives us a representative of this reduced conformal infinity. Okay, so now I can state the main theorem. It's just kind of what you would expect after everything I've led up to here. So suppose you've got an exact normalized edge metric, then given a representative of the reduced conformal infinity, so you've got to take one of these special representatives that comes from a related defining function. Then there's a unique diffeomorphism from this product into the neighborhood of the boundary. Just like before, it's the identity on the boundary. Pullback is in normal form, and the given representative of the conformal infinity is the metric that you get in the product decomposition. So it's completely analogous to the asymptotically hyperbolic theorem. I mean, you've got this conformal affinity, you pick one of the representatives, and then you get a normal form. Except that we have this extra condition. The normalized was the asymptotically hyperbolic condition on the metric, but this exactness is another condition. Okay, so this is analogous. This is what I just said. Asserts existence, and we have exactly parameterized all the normal forms. And again, this is important because in the applications, you're going to want to actually look at you want to take one normal form and put it into normal form relative to another metric in the conformal class. So, I mean, that's what's involved in all those applications I was talking about. So you really need to know what all the normal forms are and how to parameterize them. Okay, now there's one alternate way that if you're not so geometrically inclined, that's really maybe even a better way to formulate this. So I formulated this to make it look like the asymptotically hyperbolic theorem, where you choose a representative metric at infinity, but choosing that is really the same thing as just choosing one of these defining functions to first order, if it's a G-related defining function. So you can state the theorem by saying, given a G-related defining function, you can put it in the normal form so that the defining function in the normal form is the pullback of that one up to first order. And then you don't have to worry about any of the conformal affinity. Okay, so like I said, there's really just one theorem, although the proof is going to involve some interesting new ingredients. So I want to discuss a little bit about the proof here. So there's two main steps. There's also two main steps. It just follows the proof that I gave with Jack Lee in the asymptotically hyperbolic case 20-something years ago. So the first step, I'll be much more explicit about these on the next slides, is we need to solve an eikenal equation for the defining function. And the second step is once we get the right defining function, we use that to flow off the boundary to construct a diffeomorphism. So the second step, once you get the first step, the second step is exactly the same, works exactly the same way as it does in the asymptotically hyperbolic case. So I'm not going to discuss the second step. I mean, really, the whole meat of this is how do you solve this eikenal equation in this edge case. So let me motivate what this eikenal equation is. So observe that if you've got the metric in normal form, remember the normal form we just had dx squared over x squared and no cross terms with dx. So certainly the upper left thing is 1, and so everywhere, and so the product defining function is just 1 everywhere. For our normalized condition, we had to just require that for any defining function that was 1 only on the boundary. So the first step is, on the original manifold, try to change to a different defining function that agrees with the one that you had to make dx over x have norm 1 everywhere. Right? And then that's what I mean by the eikenal equation. So given a G-related defining function, we want to change it by a scale factor to make this D1 everywhere and agree with the one we had at first order. So that's the whole crux of it, is being able to do that. So this looks like a singular equation. You've got dx over x, the metric is singular, and so forth. But it turns out in the asymptotically hyperbolic case, you can reduce this to a non-characteristic first order. This is a first order equation in the new defining function. So it's some first order nonlinear PDE. And you can reduce it to just a non-characteristic initial value problem, and then it's a standard construction to reduce that to solving ODEs. So everything reduces very easily, and I'll show you on the next slide how that works and what has to change in this edge case. Let me just comment that the same proof works the same way as in the asymptotically hyperbolic case for these theta metrics, which maybe haven't been talked about here yet, but it's another class of these kinds of structured geometric structured metrics that Ray's been referring to. So this was observed and used by Guillermo and Sabaretto, and the proof is exactly the same as in the asymptotically hyperbolic case. The point is these theta metrics have the property that the corresponding vector fields all vanish at the boundary. They actually, some of them vanish to even higher than first order. And that's the fact that all the vector fields vanish at the boundary is what makes it this desingularization procedure work. And in the edge case, that's not the case anymore. The fact that these DZs don't vanish at the boundary changes the character of the problem. So you can't desingularize this the same way. So now let me be explicit about what this means. So we start with our exact normalized metric. We choose a related defining function, and we want to rescale it to make the new guy have length 1 in the edge sense. Okay, so this is the way you, this is how you desingularize the equation. You just write the new one as e to the omega times x in the asymptotic hyperbolic case. So we calculate dx hat over x hat. So it's the same thing I did before, but I'm now calling a is e to the omega. So that's what the new value is. So we just need to take the length of that and make that equal to 1. So we have to calculate the length squared of this one form. So you just, inner product, you just take the inner product with itself, you expand it out, you get the length of the first one squared, twice the inner product, and the length of the second one squared. And now we want to set that equal to 1, and then try to solve for omega. Okay? Now, the middle term is, remember, x sub x was the vector field, it was dual to dx over x with respect to the metric. And so, what that means is that if you take this vector field applied to omega, that's what this expression is. And remember also that saying that the x is g related says that x sub x vanishes at the boundary. Remember, the evaluation of that was supposed to be 0. So x sub x is a vector field that vanishes at the boundary. So anyway, we just plug that in. So I just set this equal to 1, throw the first term, the dx squared over x to the right-hand side, and just plug in whatever. So that just rewrote the equation. So this is now a vector field applied to omega plus these terms. And so let's make some observations. This is the equation we want to think about. So let's just make some observations. So the first one, I said that x sub x is big O of x because it vanishes at the boundary because x is g related. So the vector field is vanishing at the boundary. And its ratio, if you divide it by x, what you get is transverse to the boundary, and that's just because it's dual to dx over x. And so the dx part on it is non-zero at the boundary. Okay, so that's the x sub x term. Now, the right-hand side, remember that I claim the right-hand side is actually vanishing at the boundary as well. The 1 minus dx over x squared. That's not completely obvious because remember I said that's what it meant for x to be normalized, and I said that depends on x. But there's a little lemma. I'm not required that x is normalized, but there's a little lemma that says that if you've got an exact normalized metric, then any g-related defining function is automatically normalized. So it's just true with this. So now we've got left-hand side is x of x is vanishing, the right-hand side is vanishing, so what about the d omega squared term? Well, in the asymptotic, so this is just length squared with respect to the metric. In the asymptotically hyperbolic case, all the components of the metric are big O of x squared, and so the middle term has an x squared. So you divide the whole equation by x, and you've got a non-characteristic equation. Okay? So that's the whole punchline of how the proof works in the asymptotically hyperbolic case. Now, what's different in the edge case is in the length of d omega squared, we've got terms that involve the inverse metric in the z directions times z derivatives, and there's no factor to x. So we've got an equation that we cannot divide by x and desingularize it anymore. Okay, so that's the whole, you just can't do this. I've tried a lot of other ways. I kind of thought at first, there's got to be some other way. I mean, omega's vanishing at the boundary, so right, omega is x times something to get some x's, but I couldn't find a way to desingularize this. So what we need to do is to develop a new theory for first order scalar PDEs in the singular case that we can apply to this equation. Okay, so there's a new little theory. It's analogous to the theory that for non-characteristic ones, but there's some interesting things that we have to do. So the kind of equations I'm going to look at are analogs of standard non-characteristic ones. So I'm going to look at equations like this. So let me write the things here. So I'm now changing my game to just look at the model, or just a general theorem that's going to apply to the kind of equation that I just described. So we've got one real unknown function omega of x and y. So the x is still the x, and I've thrown the y's and the z's all together. Because in this part of the thing, the z's are really what's important. That was our problem in our equation. But so you can think of these as the z's as if there were no y's. But we throw them all together. So I've just got some initial condition for my scalar function, and I want to solve this equation. Now, of course, the kicker is that I've got an x dx and not just a dx on the left-hand side. So the initial surface is characteristic for this equation. Okay, so I'm going to need to assume a few things about this. Let's see. So I'm going to write the variables the q as the variable for the y derivatives there. So q is just a variable in Rn minus 1. And F is a function of those variables. So the main theorem is an existence theorem for smooth solutions of initial value problems like this. So first, I need to make a couple of assumptions. So there's one assumption that's completely obvious. If I have a solution to this equation and I restrict to x equals 0, then suppose I've got a smooth solution, then x dx of omega vanishes. The left-hand side vanishes, so the right-hand side does too, but the right-hand side only depends on the initial data. So if you plug in the initial data, which I've done here, then that has to be 0. That's a constraint on the initial data that has to be true if you're going to have a solution. So if we assume that. And the second condition is a condition that says that this is a Fuchsian kind of problem in a less obvious way than as if the right hand, if we had x dy's here. But we just require that the derivatives of f with respect to q also vanish on the initial data. And that's basically true for our model equation because the bad terms were quadratic in first derivatives of omega, and omega was vanishing at the boundary. So if you take a derivative with respect to one of those, you're always going to get a derivative of 0. So that's satisfied in our equation. Now, we need one other condition. So we've seen, for this nonlinear problem, there are analogs of indicial roots. There is an indicial, there's a first order equation. So there's one condition on what amounts to the indicial root for this equation. So I assume that if you take the partial derivative of f with respect to omega and evaluate that on the initial conditions, that's less than 1 everywhere. And that's saying that the indicial root is less than 1. That's basically what that amounts to in sort of linear intuition.
What does that mean geometrically problem?
So it's the next line. So let's state the theorem on this slide. So the theorem is under those hypotheses there exists a solution to such an initial problem here x equals 0. Okay, so this theorem will give us a solution of our Eichel equation. That's the main thing. Okay, so Rafe just asked this question. So what does this f sub omega mean? Well, let's go back and look at our equation. So remember our equation was, we had this first order vector field, a vector field applied to omega plus b omega squared. This equation is completely independent of omega. Omega, it involves first derivatives, but omega does not appear explicitly in the equation at all. So f sub omega is just identically 0 for our model, so 0 is less than 1. It's just, I could have formulated this problem without an omega at all, so it would apply to my theorem. But this is what, if you want to allow an omega to go in, this is the way you can formulate it. So okay, so the way, how do you solve initial value problems for first order scalar P's? You solve ODEs. So a nice way to formulate that is in terms of a Hamiltonian flow on a jet bundle. First jet bundle. You can say it other ways. I'll write down the equation explicitly, but say it geometrically. But the main theorem that you need to know the existence of integral curves of vector fields to solve this. So what we need is an ODE theorem about the characteristic, what I call characteristic initial curves for vector fields that will allow us to carry through the usual ODE kind of proof. So we're going to, in the next slide or two, I'm going to have set up the Hamiltonian flow out the way you solve these things. But first, let me just talk about the ODE theorem that we're going to need. So like I said, it's just like a standard ODE existence theorem for integral curves, but now everything is characteristic at the initial value. So I'm going to have to have a vector field at a 0, and I'm going to allow it to be time dependent. So now I'm changing my notation again. So I'm just talking about an ODE problem. So x is a variable in Rn, t is time. We've got a time dependent vector field, and I assume that at t equals 0, it vanishes at some point x0. Okay, so we've got a 0 at t equals 0. So a characteristic integral curve just means a curve that starts at that point, and instead of having dx dt is my vector field, it's t dx dt. So even though, if you have a 0 of a vector field and you solve an integral curve, it just sits there forever. And that's the problem with our equation. The ODEs would never move. But by allowing the t to go inside, you can have a non-trivial curve, dx dt, that solves an equation like this, even in a place where v is equal to 0, because the t makes the thing vanish. So So there's an existence theorem for these characteristic integral curves, and there's a hypothesis that depends on the linearization of the vector field. So if all of that, the eigenvalues, so dx means so a vector field near 0 has a linearization, right, which is when you first order, it defines a linear transformation of the tangent space at the 0 to first order, and that's the linearization. So we linearize the vector field at t equals 0, and if all of its eigenvalues have real part less than 1, that's an additional condition coming in again, then there's a unique smooth characteristic integral curve for any one of these vectors, any time-independent vector field like this. And so let me see. So this is the analog. This is the main thing that's going to allow us to solve this problem. And the proof is to first Taylor expand the solution to first order, to rewrite the equation in a nicer way. And then it's just a standard kind of ODE argument. When you make the Taylor expansion, you shift the characteristic exponents by 1. So the real part of lambdas all become less than 0, and you can just set up a contraction mapping theorem to prove this. Since when the eigenvalues are all less than 1, you get e to the log t times your operator it's bounded for t small, and you can just iterate and prove it kind of with standard techniques. And then standard arguments say that the solutions depend smoothly on initial conditions and so forth. Okay, so I think this is my last slide here. So now let me just indicate that the standard procedure for taking Hamiltonian flowouts to construct solutions of non-characteristic initial value problems just works with this ODE theorem as a substitute. So the first thing we do is remember, now we're going back to the PD. So omega was our scalar unknown. We're back to our coordinates x and y. And so that's my setting, my PDE theorem. So I have my initial condition omega naught. So this is my first order Taylor expansion. I just write down my initial condition and I put x times u as my new unknown. So u is the new unknown. I just Taylor expanded. I know what omega is supposed to be to start with. And now I rewrite the equation, and I get an equation for u, first order PDE for u. And now I reinterpret that on the first jet bundle, which really just means all I'm going to do is look on the space where the coordinates are x, y, u, and the first derivatives. And one of them is a scalar, the other one is a vector. So the equation, I got a single real scalar equation. So the formula you get when you make this change of variable, you write it in terms of u. We just interpret that as a Hamiltonian on the space. This is a contact Hamiltonian setting, right? Because it's not symplectic manifold, it's a contact manifold because I've got u, the equation depends on u. So that's the setting. So the contact structure, whenever you've got a Hamiltonian on a contact manifold, the contact structure gives you a Hamiltonian vector field. The initial conditions lift to an initial submanifold. The initial conditions are in the xy space, but you have the initial values, those determine the tangential derivatives, and then the transverse derivative is given to you by the equation, and that gives you a lift to the first jet bundle. And the whole, looked at this way, the fact that we've got a characteristic problem says that the Hamiltonian vector field vanishes identically on the initial submanifold. So you can't, if you did standard theory, you wouldn't have a flow out at all. Your vector field vanishes, your manifold would sit there and you'd be stuck. But we know now how to allow with these characteristic integral curves. We can, if we have the right conditions on our linearization, then we can take completely smooth integral curves associated with this Hamiltonian vector field. So you do what you normally do. You take the union of all the characteristic integral curves for the initial thing, gives the manifold one higher dimension, and then you need to show that that's just some submanifold in x, y, u, p, q space. And you need to show that it's actually the one jet of a solution, one jet of a function at all, which will then have to solve the equation because the Hamiltonian stays 0 along its flow. And to do that, this is all part of the standard proof, but now we need to use a uniqueness theorem for characteristic integral curves from an auxiliary system to show that you actually get this flow out is actually the image of a one jet of a solution. So that also requires a slightly different system, but it's the same ODE theorem, the uniqueness part of the ODE theorem. So that gives you that. So I'm quite confident, even though we haven't done it yet, or that this will have applications like geometric kinds of applications, like the thing did in the asymptotic hyperbolic case. And there's problems where it should get, but anyway, right now we need to just get the groundwork going. So, thanks.
Questions, comments? Just ask for an example. So 2 slides back, so we talked about the history of the abstract. Yeah, no, go ahead. No, go
Or the ODE theorem?
Yes. So you say there's unique theorems. So I'm a little confused. So V is, there's a T dependence, but let's suppose it's autonomous. Right. So you just have a vector field which vanishes so forth.
Right. So in the autonomous case, this vector, the solution, in the autonomous case, the unique smooth solution is 0. It's constant.
Okay, right, exactly. Gotcha. I was worried about all the integral curves that come in, but you're not talking about those. And
Right.
not on the autonomous case at 0.
That's right. When the T becomes a variable, that forces it to move.
There you go. Gotcha.
Yep.
So that's nice.
And the way that the application, the vector field, is it's a very interesting little thing the way this works. So why am I talking about time-dependent situations when there's no time in my application, the vector field is, but what happens is when you write down, so I've got an autonomous case and I'm trying to actually do this for it, but what happens is that, let me see.
The paper's down below.
I've got these up here, but I want to make sure I say something that doesn't get distracted here. Basically, one of the space variables becomes a time variable. So the PDE that you have is written in standard. The way I wrote the PDE is x dx of omega is equal to I call it f of x, y, omega, and dy of omega. So the corresponding Hamiltonian is xp minus f of all these variables, which are the q in here. Now, there's no when I write down the corresponding characteristic integral curves equation, there is no t. The Hamiltonian vector field just depends on these variables. There's no. But one of the equations that comes from this says that the partial of x with respect to t, and I'm doing a characteristic integral curve, so I do t dt of that, is supposed to be h sub p, right? So that's one of Hamilton's equations. Hamilton's equations would be without the t. dx dt is h sub p. H sub p is x in my situation. So what I've got to solve is t dx dt is equal to x. So this equation has an additional root equal to 1, because it's just as an equation for x. Do this is equal to x, you get an additional root is equal to 1. And my uniqueness theorem doesn't apply. There's 2 solutions of this one. One of them is x equals t, and one of them is x equals 0, or you can take any constant times t. So what you do here is you say, let's take the solution x equals t, and use that space variable as a new time variable, and then you apply the time-dependent Hamiltonian theorem with x as your time variable, and then you do move. You're forced to move, and that's for exactly the reason you understand. So I need the time dependence because I'm taking the space variable to be the time variable, and my vector field, my Hamiltonian vector field, really vanishes identically. And in the time independent case, as you pointed out, that means it has to just sit there forever. But since I use my t to be my x, it's required to move, and I really do get this.